The lecture today is going to be on Motzkin decomposable sets of functions. The notion of Motzkin decomposable set was very recently introduced, although the name is after Motzkin, well-known mathematician from the first half of the 20th century. The notion of Motzkin decomposable set is inspired by a result due is very well known in linear programming theory, which says that every convex polyhedron can be expressed as the sum of a polytope and a polyhedral convex cone, namely the polytope generated by the extreme points of the set and the convex cone generated by the extreme rays of the set. So these convex polyhedra are expressible as sums of a compact convex set, the polytope, plus a closed convex cone. Yeah. And the question that arises in a natural way is which are those sets which enjoy this decomposability property. We know that convex polyhedra satisfy these properties, but there is a larger class of sets, and they enjoy many nice properties which convex polyhedra enjoy. The talk is going to be based on 3 papers. These are the only 3 papers, as far as I know, in which the notion of Motzkin decomposition is used. The 3 papers are co-authored by Miguel Ángel Goberna from the University of Alicante, Spain, and Maxim Todorov from University de las Americas, Puebla, Mexico. There is also another co-author in the first paper, Enrique González, who at the time of making this paper was a PhD student of Maxim Todorov. And in the last paper there is another co-author, Alfredo Yusem from IMPA in Rio de Janeiro, Brazil. The 3 papers are in the Journal of Mathematical Analysis and Applications. The first 2 of them were published in 2010, and the last paper is already online but has not appeared in print yet. Well, so let us start with the definition of a Motzkin decomposable set. We are working with subsets of the Euclidean space Rn. We consider a non-empty set F, and we call it Motzkin decomposable if there exists a compact convex set C and a closed convex cone D such that C plus D is equal to F. Given that we are adding 2 convex sets, the sum F will be convex, and since we are adding a compact set with a closed set, the sum F will be closed. Therefore, Motzkin decomposable sets are closed convex sets, but the converse does not hold true. As it's very easy to see, and we are actually going to see it later, there are many closed convex sets which cannot be expressed as a sum of this type. When we do have such a decomposition, we call the pair CD a Motzkin decomposition of the set, and the set C will be a compact component, and the set D will be the conic component. I say the conic component because it is uniquely determined by the set, unlike a compact component. There may be many compact components, actually infinitely many compact components for a given set, but there is only one possible conic component, which is the recession cone of F, namely the set of all directions along which if you follow one starting from an arbitrary point of the set, you never leave the set. This is a large class of closed convex sets. As I said at the beginning, it includes all convex polyhedra, but it also includes all compact convex sets, because we can take D equal to the singleton of 0. It also includes all closed convex cone, because we can take C equal to the singleton of 0. Then it's a large class, but it doesn't exhaust the whole class of closed convex sets. We can now define an extended real valued function to be Motzkin decomposable when it has a Motzkin decomposable epigraph. For some characterizations, this set plays an important role. This is the closed convex hull of the extreme points of the intersection of the set with the orthogonal subspace to the linearity space of F. The linearity space of F is the set of all directions corresponding to lines which are fully contained in the set, or in other words, is the intersection of the recession cone with the opposite. We need to consider this intersection because we want to talk about extreme points, and it is well known that a closed convex set has at least one extreme point if and only if it has no lines. That is to say, if and only if the linearity space of F reduces to 0. So in this particular case, when there are no lines, this linearity space reduces to 0, the orthogonal is the whole space, so the intersection here is superfluous, the intersection gives F. So in that case, Q of F will simply be the closed convex hull of the set of the extreme points of F. But even if there are no extreme points, we are considering extreme points of a smaller set thanks to this trick. We can call this intersection the lines-free version of F. We have here first a characterization of Motzkin decomposability for a non-empty closed convex set. A set F being non-empty, closed and convex is Motzkin decomposable if only if the set of extreme points of the lines-free version of F is bounded, and in this case the set Q of F, which we have seen before, namely the closed convex hull of this set of extreme points, is a compact component of F. But as I said before, there may be many compact components, but in the case when the set has no lines, this compact component is the smallest possible. Conic component is unique.
More than one compact component, but
yes,
the cone component is unique.
Yeah, is unique, but compact component there be many.
Okay.
But in the case there are no extreme points, among the many, this is the smallest possible. If there are lines, there is no smallest possible, even there is no minimal one with respect to inclusion. Okay. Well, as a corollary of this theorem, we have that every phase of a Motzkin decomposable set, it's Motzkin decomposable too. This comes from two facts. First, that the linearity space of a phase is the same as the linearity space of the whole set. And second, that one can easily check, the lines-free version of a phase is a phase of the lines-free version of the set. And then the extreme points of the lines-free version of the phase will be extreme points of the lines-free version of the set. If the set is bounded, then this subset will be bounded too. Hence, we have the corollary as an immediate conclusion. Another immediate conclusion is this last corollary here, that if we have a Motzkin decomposable function which is bounded from below, then the set of its global minima is Motzkin decomposable. And notice that Motzkin decomposable implies non-emptiness. Every Motzkin decomposable set is non-empty. So here in particular we are saying that whenever a Motzkin decomposable function is bounded from below, it attains the infimum, it attains a minimum. This property is well known for polyhedral convex functions.
It's something like a Frank-Wolf theorem.
For quadratic programming. Yeah. But I mean, this is a direct generalization of what is known in linear programming. I forgot to say that a polyhedral convex function is Motzkin decomposable, because a polyhedral convex function, which is the maximum of a finite collection of affine functions, has an epigraph which is a convex polyhedron, and therefore it's Motzkin decomposable. So this class of functions, Motzkin decomposable, contain in particular the polyhedral convex functions. They also contain sublinear functions, because sublinear functions have an epigraph which is a closed convex cone.
Yeah.
So again, this result follows from the main theorem because one can easily identify the set of global minima with a face of the polyhedron, of the epigraph of the function. There are some questions we can make to understand the structure of Motzkin decomposable functions. For instance, consider the restriction of one sun function to a hyperplane. Is it necessarily Motzkin decomposable? Well, first of all, we need to make the question more precise. Since we are dealing all the time with functions defined on the hull of Rn, when we make the restriction with a hyperplane, we are no longer working with a function having full domain. So we have to extend the restriction to the complement of the hyperplane, and we do it by the value plus infinity. Okay, so the restriction is actually the function which is obtained from the original function by replacing the values the function takes outside H by plus infinity. So is such a restriction Motzkin decomposable?
Can you stop for a second? I'll go to the bathroom. The lights are too much. I can't take the eyes. I'm feeling very. It's too much of light. Can the light be dimmed a bit? I'm feeling too much disturbed with lights.
We were addressing the question whether the restriction of a Motzkin decomposable function to a hyperplane is necessarily Motzkin decomposable, and the answer is no. Here we have an easy example in 2 dimensions, a function of 2 variables, the Euclidean norm. The Euclidean norm is Motzkin decomposable because its epigraph is the classical ice cream cone. As long as it is a closed convex cone, it's Motzkin decomposable. Nevertheless, if you take as the hyperplane a vertical hyperplane, not containing the origin, not containing the vertex of the cone, then what would be the restriction of this function to this hyperplane? The epigraph of this restriction would be the area enclosed by a branch of a hyperbola, which is not Motzkin decomposable because the set of extreme points is the whole boundary, which is unbounded. Therefore, it cannot be, according to the theorem we saw below, cannot be Motzkin decomposable. But if the hyperplane is a supporting hyperplane to the domain of the function, then the restriction is Motzkin decomposable. The reason is that in that case, the epigraph of the restriction would be a face of the epigraph of the whole function, and then it would be Motzkin decomposable. There are several questions we can address related to operations with Motzkin decomposable sets. Here is one. Suppose we have 2 closed convex sets, A and B, and one of them, say B, is Motzkin decomposable. And when we make the sum is Motzkin decomposable too. Can we deduce from this fact that the other set, A, is Motzkin decomposable too? The answer is no, as I will show by an easy example soon. But the answer is yes, if we impose the additional assumption that the recession cone of the set B is contained in the linearity space of A. To see that without this assumption the property does not hold, look at this example here. The set A is, let's say, a vertical parabola. Okay, the area enclosed by a vertical parabola. Okay, we can make a picture if. This would be A. Then the set B is the horizontal axis. And what is A plus B?
Yep.
A plus B would be the full upper
thing except this line.
no, including this line.
Oh, acha, set is x2.
You are
the whole thing, whole half space.
Is the whole
upper half space.
Upper half plane. Then you have B is Motzkin decomposable because it's a closed convex cone. It's a subspace. The same with A plus B. It's a half plane, so it's also Motzkin decomposable. Nevertheless, our original set A, the parabola, is not Motzkin decomposable for the same reason as we saw before in an example. The set of extreme points is unbounded, is the whole boundary. Of course, in this case,
here the case B is not bounded.
Yeah, but it doesn't matter. The condition, the result, as you can see here, is that we are assuming that both B and A plus B are Motzkin decomposable.
B and A plus B are
B is the horizontal axis, A plus B is the upper half plane.
So that the recession cone,
but we don't
in
have
the
this
linear
inclusion, of course. This is not contained in the linearity space of A because the recession cone of B is the whole of B.
Yeah.
And the linearity space of A reduces to 0. A contains no lines, so the inclusion does not hold. This shows that this extra assumption in the proposition is not superfluous. But in particular, if the set B is bounded, is compact, then the recession cone reduces to 0 and it will be contained in the linearity space of A. So in such a case, the property holds. This is what is said in this corollary at the bottom of the page, in which on top of these assumptions, there is some refinement. We are not assuming that A and B are closed. A and B are just convex, and B is bounded, but we don't say closed or compact. Then, in spite of these weaker assumptions, we get the same conclusion. If A plus B is Motzkin decomposable, then A must be Motzkin decomposable. This is based on this lemma, which is a very easy statement in convexity, but which the proof of which is not completely obvious. I wouldn't say it's an exercise. It's not terribly difficult, but it's not a standard proof in convexity. It says if we have two non-empty sets such that A is convex, just convex, B is compact, just compact, and A plus B is closed, then A must be closed. Just one observation, this result doesn't hold true without convexity of A. For instance, consider any set which is dense but different from the whole set, Rn, then add the unit ball or a ball of arbitrarily small radius, closed ball which is compact, then A plus B is the whole space, then it is closed. Nevertheless, A was not closed, was a dense subset. Also with convexity, this result only holds true in finite dimensions. In an infinite dimensional space, it doesn't hold true. Consider, for instance, a reflexive Banach space with the weak topology. Then you can repeat the argument I have used now by choosing a dense hyperplane, which is convex. Then you add a closed ball, which is compact under the weak topology. Then you get the whole space, and you repeat the argument I have used before. But even recently, 1 week ago, Professor Nicolas Hatchisavas gave me a very nice example showing that even in an arbitrary Banach space, not necessarily reflexive, and using the norm topology, not the weak topology, this result does not hold. I mean, we can take this result as a characterization of finite dimensionality. This result holds true if and only if the space is finite dimensional. Well, I'm going to present several characterizations. We have seen already some of Motzkin decomposability. One of them will be based on the notion of the conic representation of a non-empty closed convex set. The conic representation K of F is, roughly speaking, the set of all linear inequalities which are satisfied by all the elements in F. Okay, so we consider all coefficient vectors A, B in Rn plus 1 corresponding to inequalities which are satisfied by all vectors in F, all points in F, and then the set of all these coefficients make the conic representation of F. Clearly, this is a closed convex cone. Yes?
Semi-definite programming, semi-infinite programming.
This is a notion which I don't know if it was introduced, but at least is extensively used in linear semi-infinite programming. Yeah.
Oh.
Yeah, this is very much used in that field. Then, for instance, it is well known, in fact, this is a version of Farkas' lemma, that if our closed convex set is the solution set of a given linear inequality system, with possibly infinitely many inequalities, we are not saying anything here about the cardinality of T, then the conic representation is the closed convex cone generated by all the inequalities, let's say, together with this particular vector. All components are 0 except the last one, which is -1, the closed convex hull of all these vectors. The reason for which this particular vector appears is that there is always a trivial inequality which is a consequence of a given system of inequalities. Notice another way of looking at this K of F in this case is the set of all consequences, linear consequences of this linear system. Okay, and there is also a consequence which is which trivially holds, namely you have the inequality 0n prime transpose x, we are saying greater than or equal to -1. Okay, this clearly holds true for every x, and this is the reason why this vector appears here. Or in other words, if you have an inequality a prime x greater than or equal to b, you can always decrease the right hand side and it will be a valid inequality. The conic representation is in fact minus the epigraph of the support function of the set. We also have that a point belongs to the set if and only if, when we add a last coordinate -1, then the resulting point belongs to the dual cone, positive polar, of the conic representation of the set. And moreover, for every vector in this polar set, dual cone, the last coordinate is less than or equal to 0. The barrier cone of F, which means the set of all linear functionals which are bounded above on F, is minus this set. By K of F head, we mean the projection of K of F onto Rn. K of F is in Rn plus 1. We delete the last coordinate when we get the projection onto Rn. This is the meaning of this expression here. And we also have that the recession cone of F is just the dual cone of this projection. Moreover, F contains no lines, or in other words, F contains some extreme point if and only if the interior of this projection is non-empty. The affine set, the affine hull of F is the set of points which solve all this system of equalities, where the equations are taken from the linearity space of the conic representation of F. Also, the boundary of F can be expressed in terms of the conic representation in this way. I have to explain here the notation. Here F star of C denotes the arcmean of the linear function C over F. So this is arcmean over F of C prime x. So in fact, what this property is telling us is that the boundary is a union of exposed faces. Moreover, an optimal point for the linear function determined by C is such that this point belongs to the conic representation of f and vice versa. Moreover, for C in the interior of this projection, this optimal solution set is non-empty, and this does not imply that C is in the interior of the projection, but C must belong to the projection. Some easy calculus rules for conic representations. The conic representation of the closed convex hull of a union is the intersection of the conic representations of the set, and for the intersection is the closure of the sum. Moreover, if the two conic representations have this property that the intersection is a linear subspace, the intersection of one with minus the other, then this formula simplifies, the closure becomes superfluous, and the conic representation of the intersection in that particular case reduces to the sum of the conic representations of the set. When the second set G is a closed convex cone, we have this equality, which gives us an expression for the conic representation of the sum. And in particular, we have this intersection when f intersection with minus G is non-empty. We have also an expression for the conic representation of the linear image of a closed convex set under the assumption that this linear image is closed. One can characterize closed convex sets which are cones by using the conic representations. They are those closed convex cones for which the conic representation has this structure. Is a Cartesian product where the second component is the non-positive real line, and if such thing occurs, then the first set in this Cartesian product must be the dual cone to f. We also have this proposition which summarizes many properties of convex Motzkin decompositions of a set. Suppose we have one such decomposition, then the conic representation of f is the conic representation of C intersection this set, where D is the conic component, so the recession cone. Also, we have that the affine hull of the set is the affine hull of a compact component plus the linear space generated by the conic component. If we have a linear mapping such that the image of the recession cone is closed, then the images of the compact component and the conic component make a Motzkin decomposition of the image of f and that linear mapping. Fourth property is important because it deals with solution sets of linear problems subject to nonlinear constraints, x belong to f. This property says that whenever a linear function c prime x is bounded below on f, that is to say when the infimum is not minus infinity, then it is attained, it's a minimum. And this happens when C belongs to the dual cone to D, if and only if.
Yep. I just want to, so the fourth property, which is very interesting from the optimization point of view. So you are minimizing a convex set over a Motzkin decomposable set.
A linear function over a Motzkin decomposable
linear function over a Motzkin decomposable set, and if it is bounded below, then the minimum is attained.
Yeah.
C is element of D naught. So if C is element of D naught, we can guarantee that it is bounded below?
Yes. For a Motzkin decomposable set.
But I have one question. The second line says minimum C transpose x, x belonging to C, or it should be x belonging to F.
Where?
VC, when you are writing mean, when you are replacing the inf with mean.
No, it's C, it's equivalent. Thank you for pointing this out because it's an important observation. In principle, the function is defined over F. I mean, we are minimizing over F.
Yeah.
But this says that there is at least one point in C where the minimum is attained. There is no typo here.
No, there is not. I understand. Every element in C is also an element in F, because you can add C plus 0. Because
every element in C is an element in F. C is always a subset of F.
So, okay, the interesting part is the minimum would be attained on C.
Not
on the cone. Only on the compact part the minimum would be attained.
No, the minimum can be attained everywhere, but among the optimal solutions there is at least one which belongs to C.
Okay, achha, among the optimal, right. If C belongs to D.
Like in linear programming, among the optimal solution there is a vertex.
Yeah,
that is to say, belonging to the compact component.
Yeah, right, okay.
Yeah. The fifth property is also interesting. It says that the barrier cone is minus the dual cone to the recession cone. It's interesting. Why? Because it's telling us in particular that the barrier cone is closed, which is not always the case in general. I mean,
barrier cone is not closed.
But actually sets with a closed barrier cone have been already studied. They are called hyperbolic convex sets. So this shows something which is actually an immediate consequence of the definitions, that every Motzkin decomposable set is a hyperbolic convex set. The sixth property is that the set contains no lines if and only if the interior to its dual cone is non-empty. Seventh property is that the boundary of F is the union of the exposed faces determined that elements belonging to the dual cone to the recession cone except the origin. In the two-dimensional case, a Motzkin decomposable set has no asymptote. Here we define asymptote as a half line which doesn't intersect the set, but its distance to the set is equal to 0. That means you can find points arbitrarily close to each other, one in the set, one in the line, but they don't intersect. So one can prove that this holds in R2, but the convex doesn't hold true even in R2. I mean, the fact that there is no asymptote does not guarantee that the set is Motzkin decomposable. Example, take the parabola. There is no asymptote. It's a closed convex set, but the extreme points is the whole boundary. So it's unbounded, so it cannot be Motzkin decomposable. What about higher dimensions? The statement which was true, namely that a Motzkin decomposable set has no asymptote, does it hold true in higher dimensions? The answer is no. Look at this example. We are considering a cone. This is a cone, and if you take the intersection with this hyperplane, it has two asymptotes, and of course the asymptotes of a subset, as long as they don't intersect the set, are asymptotes of the set. Look at this example in dimension 3. Actually, we have seen this for a different purpose before, when we were talking about the restriction to a hyperplane. Again, take, so this cone in the case n equal 3 is the ice cream cone. Okay? Then take a vertical hyperplane as before, not containing the origin. The intersection is a hyperbola which has asymptotes, and the asymptotes of the hyperbola will be asymptotes of the cone. This is not very, this is very obvious after listening the explanation, but if I don't make the explanation and I ask you which does this set have asymptotes, intuitively at least I would answer no, because I mean it consists of lines.
Whether it will have asymptotes.
Yeah.
That to 2.
But
yeah, now I understand. Yeah.
But it has. So in the case n equal 3 or higher than 3, it doesn't hold. Another result is that a set is Motzkin decomposable if and only if there is a set C such that whenever we have a linear function bounded from below on C, then, as you observed before, there is an optimal solution of the corresponding minimization problem with this linear function, which belongs to C, to the compact component. If such a set exists, we know that the set is Motzkin decomposable, and the closed convex hull of this set is a compact component of F. Another characterization, I said that Motzkin decomposable sets are hyperbolic, means the barrier cone is closed, but the converse doesn't hold true. We need an extra assumption. We need the restriction of the support function of the set to the barrier cone to have a finite sublinear extension to the hull of array.
I just like to recall just the barrier cone definition. Barrier cone is the
set of linear functions which are bounded above on the set.
Barrier cone.
Barrier cone. I mean, you are moving a hyperplane in this direction. If you cannot go beyond, the corresponding orthogonal vector pointing in this direction is an element of the barrier cone.
No, there is some relation, some polarity relation with some other set.
Yes, with the recession cone.
Yeah, exactly. The
recession cone is the polar of the barrier cone.
Exactly.
But if you take polar again, you don't get the barrier cone. You get the closure of the barrier cone.
You don't have closeness.
Pardon me?
Polar of the recession cone is the barrier cone.
No, it's the closure of the barrier cone in general. The closure of the barrier cone.
The polar of the barrier cone is the recession cone.
This is true.
Yeah, because barrier cone is not closed, so you cannot have. Yeah.
When it is closed, you call the set hyperbolic.
Yeah.
And our Motzkin decomposable sets are hyperbolic, but a hyperbolic convex set need not be Motzkin decomposable. One needs an extra condition, which is this one: the support function has a restriction to the barrier cone, which has a finite valued everywhere, finite valued sublinear extension to the hull of Rn. What is this finite sublinear extension? Is the support function of a compact component. This is very easy to understand. I have no time to give more explanations, but this is not a difficult result to obtain. Another characterization of Motzkin decomposability in terms of conic representations. A set is Motzkin decomposable if and only if there exist two closed convex cones K and L such that the conic component, the conic representation of the set has this structure. K, L and L are closed convex cone. And the first convex cone K doesn't contain this element, this vertical vector upwards, and the interior of the cone contains this vertical vector which is downwards. Another set which is important for the description of Motzkin decomposable sets is the set M of F defined here. We call L the orthogonal to the linearity space of F. We call K the intersection of the recession cone with L. This makes K pointed. In general, the recession cone of F contains lines, but when we make this intersection, the intersection does not contain lines anymore. Then now we consider this set which can be easily seen, that is nothing but the efficient points of the set F with respect to the ordering induced by K. Then, if and only if this set is bounded, the set is Motzkin decomposable. And in such a case, the closed convex hull of this set is a compact component of the set. And in the case when our Motzkin decomposable sets contains no lines, this closed convex hull coincides with the closed convex hull of the extreme points, the set Q of F which we saw at the beginning of the talk. This means this is the smallest compact component in such a particular case when there are no lines. Still another representation or characterization of Motzkin decomposable sets in terms, this time not of the conic representation, but of linear representations of the conic representation. F is Motzkin decomposable if and only if there is some linear representation of the conic representation of F such that this set of coefficients, normalized coefficients we could say, is bounded, and in which case we have here a specific Motzkin decomposition of the set. Unfortunately, Motzkin decomposable sets do not enjoy many nice calculus rules. We saw before that we make the intersection. We are going to repeat this later, and the intersection may fail to be Motzkin decomposable. Here we have the same with the sums. The problem is that when we are the cones they are closed by definition, but the sum may fail to be closed. We have no problem when adding the compact components, but when adding the conic components there is a problem. But this problem disappears if we use this assumption that whenever we have a sum of elements, each one belonging to the recession cone of one of the sets, and this sum is equal to 0, then the elements must belong to the linearity space of the sets. In this case, the sum is Motzkin decomposable. And this is the example as I was mentioning before. Once more, we see the ice cream cone. We see here a vertical hyperplane not containing the origin. We make the intersection, and the intersection we have seen already twice. That is not Motzkin decomposable. So there is this unpleasant property that the intersection of Motzkin decomposable sets is not necessarily Motzkin decomposable. In the last part of my presentation, I am going to talk about a special kind of Motzkin decompositions obtained by so-called truncations. To explain the idea very easily is, okay, we have a closed convex set, Motzkin decomposable or not. We take a hyperplane, okay, and well, in this particular example, we have two truncations, which are the intersections with the two half spaces, and one of them happens to be compact. Okay, well, it turns out that
how many truncations here? The set is divided into two parts.
The truncation is, look at the definition here. We take a hyperplane which intersects the set.
Okay.
This intersection we call the slice of the set induced by the hyperplane, and we consider the two closed half spaces determined by H. These two half spaces determine two intersections which are called the truncations. Okay, if one of these truncations happens to be compact, not only compact but a compact component, means that when you add the recession cone you get the whole of the set, then we say that we have a Motzkin decomposition of type T, of the truncation type. So these are decompositions obtained in a very particular way. Then a first question to address is, when does a hyperplane inducing a non-empty slice induce a Motzkin decomposition of type T? The answer is when one of the closed half spaces determined by H is compact. This is obviously a necessary condition, but this compact truncation contains all the extreme points of the set.
Yeah, then only you can have.
If and only if.
Then only you can have that decomposition. That
Yes.
is quite intuitively clear. Otherwise.
Yes, exactly. And notice that an immediate consequence of this proposition is that if the set admits Motzkin decomposition of type T, it can contain no lines. If it contains one line, it's impossible to have a compact truncation. Very easy to prove. Okay. Well, we need to introduce here some notation which will be used later, but first an observation is that when the a truncation has a smaller dimension than the set, the truncation coincides with the slice. Or in other words, if the slice is properly contained in the truncation, the dimension of the truncation must be exactly the same as the dimension of the space. The question now is, when a half space induces a compact truncation, and here you have the answer, if and only if the vector belongs to the interior to the dual of the recession cone, if the half space is defined with less than or equal to, or to minus the set if it is defined the other way around. Then we also have that the slice is compact and F contains no lines if and only if A belongs to one of these two sets. This result has several consequences. The first one is that if we have a set without lines, then for a hyperplane inducing a non-empty slice, the slice is compact if and only if at least one of the two truncations induced by H is compact. We saw before that if there is a compact truncation, there can be no lines. But now from these results, it follows that the converse holds true. There is a compact truncation if and only if there are no lines. I'm not talking about Motzkin decomposition of type T. I'm just talking about compact truncations.
Oh yeah, I understand.
Which is different. In particular, when we apply one of the results we have seen before to functions, we get that for a lower semi-continuous proper convex function, inf compactness, which means that the lower level sets are compact, occurs if and only if this particular vector belongs to the interior to the dual cone of the recession cone of the epigraph of the function. When does a set have compact slices? If it contains no lines, it always has compact slices, and the converse holds true in dimension 2 or higher if the interior of the recession cone is non-empty. In dimension 1, this is clearly not true, and one can also give examples showing that it doesn't hold true if the recession cone has an empty interior. When F contains lines, it contains compact slices in just a very special case, when it is Motzkin decomposable and the recession cone is exactly one line, one whole line. There is no other possibility. Now, how to characterize Motzkin decomposable sets by means of truncations? First, an observation. If we have a compact decomposition of type T, this is what we have here, a truncation which is compact plus the recession cone, then the possibly unbounded truncation is also Motzkin decomposable, with the compact component being the slice. After this observation, we can make this statement, which says that a closed convex set is Motzkin decomposable if and only if for every element in this set we have this decomposition. We are not saying this is a Motzkin decomposition of type T. We are saying we have this expression. If this expression holds for every A in this set, F is Motzkin decomposable, and in fact it is sufficient to have just one element in this set which is smaller than that one for having Motzkin decomposability, that is to say, for having this property for every element in the larger set. When we translate these results for functions, we get that if we consider a function with compact domain, then this function is Motzkin decomposable if and only if the function is bounded on its domain. Bounded here means bounded above, because bounded below is automatically the case, because we are dealing with a lower semi-continuous function on a compact set. This is when the domain is compact. We later on consider the general case, or a more general case, but first a proposition which we will apply for that result. If we have an unbounded closed convex set containing no lines, if H is a hyperplane and H plus is one of the half spaces determined by H, then this half space is a union of closed half lines emanating from edge if and only if the set of the extreme points of the truncation is contained in the slice. This will be used next. To prove this theorem, a set is Motzkin decomposable if and only if there is a hyperplane such that one of the truncations induced by H is compact and the other one is a union of closed half lines emanating from H. And from here it is very easy to prove that if a set is Motzkin decomposable, then it has a Motzkin decomposition of type T. Applying the previous result to functions, we have that if the domain of the function contains no lines, then Motzkin decomposability means two things. First, that the function is inf-compact, or lower level sets are compact. But then there is one level, alpha, such that on the complement of that level set, of that lower level set, we have a union of half lines on each of which the restriction of F is affine. And I will finish by presenting just one result about smallest Motzkin decompositions of type T. Suppose for a Motzkin decomposable set there is a smallest compact T component. I mean, there is a Motzkin decomposition for which the compact component is the smallest among all possible compact components belonging to a Motzkin decomposition of type T. Then this smallest compact T component is the smallest in the larger set of all possible compact components of Motzkin decompositions, whether they are or type T or not. But we have an example in 3 dimensions which shows that in some cases there is a smallest compact component which is not of type T. This means that for a closed convex set without lines there is a smallest compact T component if and only if it is the smallest component among all, but we know that the smallest compact component among all is Q of F. So if and only if Q of F is obtained by truncation, Q of F, I recall, is the closed convex hull of the extreme points of the set. Okay? So if this closed convex hull is obtained, can be obtained by truncation, then this is, we know, the smallest compact component, then it is the smallest compact T component. So if and only if this happens, one smallest compact T component exists, but there are examples in which a smallest compact component exists, but it's not obtained by truncation, then it's not, there is no smallest, even not a minimal compact T component. And this is the end of my presentation.